Yeah, lecture 1 is a review. So this is last semester for some of you, a couple years ago for a few of you. So if it's been a minute or it feels like it's been a minute, this one's for you. We're going to wade our way in. So this is serving two purposes. The real purpose is to get you used to hearing about this from me. Because if you had someone else for regression, they may have used different words and different notation, and I want to kind of get us all on the same page with something that you're familiar with before we introduce things that you're unfamiliar with. So this should be mostly a review. The part that might be less of a review is interaction terms. I hit those very hard when I teach intermediate, and not everyone does. So this might be new, and it might not be. But I have a way of making it less painful than it might otherwise be. That's my plan. All right, so naming conventions. Here's an organizational scheme to your question about univariate versus multivariate. So the general linear model is what this lecture is reviewing, what you should be familiar with. It is designed for independent observations in the univariate case. So univariate means one outcome at the same time. ANOVA is if the predictors are categorical. That stands for what? Remember this word?
Analysis of variance.
Analysis of variance, which is the dumbest name ever because it's an analysis of means. It is. That's the whole point of ANOVA, is mean differences. So why is it not analysis of mean or whatever? Regression is what it's called if you have quantitative predictors. If you have both, it may be called ANCOVA, analysis of covariance, or if you allow them to interact, then it's just called regression. Multivariate versions, they're using least squares. MANOVA is what it's called if you have multiple outcomes and categorical predictors. MANOVA is unstructured, by the way. Crossover events for those of you who've been through longitudinal, I'm pointing at you. Multivariate regression is what it's called if you have multiple outcomes and multiple predictors, and then MANCOVA if you have these things. So that's how these labels are organized. The thing they have in common is that they all say that the residuals that remain after you put all your predictors in the model should have a normal distribution, because sums of squares land is essentially using normal as its formula for height. Minimizing the e's is the same thing as maximizing the likelihood. You can think of it from either perspective. By the way, predictors do not have distributional assumptions. Predictors do not have to be normally distributed. They can be whatever they are. Otherwise, ANOVA couldn't be a thing, because those are categories, not normal. The use of these labels usually implies the least of ordinary least squares estimation in particular. So let's review. So empty model is what we did first last semester. That's what we're going to do first this semester too. That's what we're going to do first in every class I teach, pretty much. Empty means no predictors. So what this should do is return back to you the mean and the variance of an outcome. Beta 0, that's my fixed intercept. If I know nothing else about a person, what's my best guess for their outcome going to be?
Go what you know.
If I know nothing else about a person, what's beta 0 going to be? What would be a good guess?
Mean.
The mean, yeah. Something in the middle. But the mean in this case. So in this picture, the empty model prediction is given by this purple line, because I don't have my x-axis as part of the story yet. So beta 0 is the mean of this variable. What we're predicting in this example is income in thousands of dollars. Yes, this is a throwback from last semester, but we're not going to analyze those data anymore, I promise. Income in thousands of dollars. So in this sample, the average income was $17,300. Well, what if I want to predict income for this person up here? Their income was actually $58,800. So this is not a good guess for them. So their residual, the E, that's how far off, how wrong the model is for that person, works out to be 41.5. That gets us to their original value. So each prediction is going to be wrong to some extent, unless you are literally at 17.3. So inside this parenthesis, what I have is your actual outcome, y sub I, minus y hat, which is the one that's predicted by the model. Right now, the model is just beta 0. So then we square those. Why do we do that?
All positive.
Exactly. We don't want the positives and negatives to cancel. Once had someone ask me why not take the absolute value. The function is pointy, is the answer to that. This creates a parabola that you can find where the top or the bottom is, depending on how you think of it. So it makes the math easier is the short answer. Absolute value will come back later in the semester in quantile regression. So each person's E is what's in here. We square it. We sum it over people. We divide by n minus 1. Y minus 1. Do you remember that? Because, yep, we had to know what the intercept is to do this. Said differently, I got n problems, but the mean ain't 1. How about that? So 190.2 is the result in this data set of going through this. So that's all the variability in income that there is. So this semester, we're not going to have this anymore. It's gone. I know, bye-bye. But income is probably related to stuff like, I don't know, education, right? We're all here because we want to get better jobs, make more money, make a difference, all that fun stuff. Live indoors, buy the good toilet paper at Costco. You know, hashtag goals. So let's put in education. Now this x-axis is labeled education and then 0 equals 12 years because I have subtracted 12. What is that called?
Shift.
A shift?
Centering.
Centering. Yep, we're shifting x. Why are we shifting x?
Does it want to be able to make a valid interpretation?
Yeah, because otherwise beta 0 is our expected outcome when the predictors are 0, right? So if I didn't move x, then I would be predicting income for someone who never went to any school at all. I don't have anybody like that in my data set even, and it's kind of a weird thing to predict. So I picked 12 because that stands for high school degree in the US educational system. So now beta 0 is the expected income for someone who graduated high school. In this sample, they're expected to make $14,000. Not great, but you know, better than nothing. So then that gets me to this point right here on the regression line where 0 is the middle. The slope of this line relating education to income is 1.8 in this data set. For this person up here, I'm putting in an 8 because they went to 20th grade. And 20 is 8 more than 12. So if I put in 20 minus 12, I get the 8. That's where this is like that. So this semester, we're going to be centering everything for the same reasons. We want to have meaningful intercepts. Do the math. They're predicted to have an income of 28.4. That gets me to this spot on the blue line. Better, closer, heading in the right direction. Not there yet. Still wrong. Still wrong by 30. So what we've done is essentially carve up the difference between where each data point is and the naive line given by the mean into what we call explained, meaning, oh, I know why this person makes so much more money. They went to 20th grade. But that's clearly not all the story because they would have been here if that's it. So what else is it about them that allows them to make big bucks, relatively speaking? Don't know. Unexplained is everything that's left. So, go ahead.
So why is I feel as if I'm having to understand empty model. What's the difference between an empty model and just the mean of an outcome?
Nothing.
Oh, okay.
Nothing at all. I do this pedagogically to set up the idea that the variance, the residual variance in this model is all the variance that you have.
Oh, okay.
Now, in our class, we're going to do this for a different reason. We're going to do this to figure out what the hell y is. Because if I know I should get the mean back, then, for instance, in predicting binary data, some software defaults to predicting the proportion of ones. Other software defaults to predicting the proportion of zeros. How do you know which you're doing? I should get a number back that I should be able to back translate into either of those numbers, and then I'll know which way the model's up, which way it's going. So I do that as a sanity check in this class. It's surprisingly difficult to reconcile across different software packages. It really is. But yes, this should be the mean. And so now you can think of y hat as a mean, but it's a conditional mean because everybody who went to 20th grade has the same expected income. So it's conditional on education, but it's still a mean because it's in an aggregate. Now, to the extent that the slope of this blue line is not flat, that we do a better job predicting income after accounting for this information, what should happen to this 190? Up, down, or stay the same? Got one vote for down. What should happen to the variance if education is related to income? Should this go up, down, or stay the same?
Down.
Should go down. Like, it can't go up, actually. That should not happen. Something went wrong if it went up. Stays the same is like the worst case scenario in least squares land. That is not true in maximum likelihood land. It actually can go up. But yeah, after switching the prediction from the purple line to the blue line, the e's collectively are smaller. And it works out that if I just compute the proportion reduction, that's known as adjusted R-square. 17.17 is the proportion explained by education in this example. So this is an example of what we're not going to be able to do this semester because we don't have variance. The normal distribution has one parameter for estimated variance, and it's supposed to hold for everyone. In non-linear link function land with different distributions, that's not true. So more generally in notation, things that have an I on them are variables, and they are measured in this class exclusively. Things without an I, like that are in red, these are fixed effects, they are constants. So everybody has the same beta 0 applied to creating their score. Everybody has the same beta 1. They are fixed. They are constants. P in this case is the number of predictors, so we could put in as many as we want. So then in this case, beta 0 is my intercept, expected y when all the predictors are 0. Each of these is slopes for the change in y for a 1 unit change in x. I tend to say difference because people aren't changing into each other. It's maybe a semantic distinction, but to someone who specializes in longitudinal analysis, it's not. So you'll hear me say difference instead. Each fixed slope has a bunch of things that come with it in your output, and only 2 of them are essential to report. So we're going to review some vocabulary. The estimate, that's the answer. That's the best guess for what the slope should be using our data. It is the answer that made our data collectively the tallest. Synonyms for estimate are coefficient. You will also hear point estimate, meaning at that point, one number. This is the number that made my data the tallest, the coefficient point estimate, otherwise known as the answer. Next to it is a standard error. I beat you guys over the head with this last semester.
And then some.
Sorry, not sorry.
Oh.
Standard errors tell us how inconsistent our results would be across repeated samples of the same kind. They're an index of inconsistency. More specifically, it is how far wrong your slope is from the population slope on average. That's what it's supposed to tell you. Wiggliness is an idea. So if my slope is 3 and my standard error is like 0.5, I have a lot more certainty that 3 is really a good answer than if my slope were 3 and the standard error were 3. Because then it's like, I have no idea what this could be. Could be 3, could be 6, could be 9, could be 0, no idea. These 2 you need to report because everything else is derived from these. Next will be estimate divided by standard error. Used to be called T. It's going to be called Z this semester. Estimate minus what the estimate was supposed to be, null hypothesis. It's almost always 0, so that's why I shorten it to estimate over standard error. This tells you how unexpected your slope is against the null hypothesis. So is 3 far away from 0? It seems farther away if the standard error is smaller than if it's larger. So estimate minus what it's supposed to be is the null hypothesis divided by standard error is a test statistic that we then compare against a distribution. And by we, I mean the software. We're not doing any of this. We're not looking up p-values. We're not doing any of that stuff. Next over, denominator degrees of freedom. That's sample size, big N, minus k for the number of fixed effects. So you saw this in the formula for variance, n minus 1, right? The 1 was because you had to know the mean. If I add a predictor, can you guess what it's going to be?
N minus 2, like
N minus 2. And if I add another predictor, n minus 3. So how many parameters can I have? Up to n minus 1. Like, that's how many. So this tells me how many more things I have room to add to my model. This is gone after this day 2. Yep. These models are using infinite sample size, z's and chi-squares. P-value. People love to misinterpret this, but we're not going to be those people. It is the probability of finding a result as extreme if the null hypothesis is true. How unexpected is this? And we typically use a cutoff, what's known as an alpha level of 0.05 in the social sciences. That means we're willing to be wrong 1 time out of 20, that we declared something really unexpected, but it wasn't really that unexpected. So estimate divided by standard error gets the test statistic. If I know the degrees of freedom, then I know the exact p-value from this. So I don't need to report these things. You can report the p-value, or you can make stars for it if you want to do it that way. Confidence intervals. This is what you got plus or minus expected range of fluctuation as given by the standard error, and whatever level of confidence you want. So it'd be 1.96 if you want 95%, for instance. I don't like these. I don't find them helpful. But if your confidence interval overlaps 0, your p-value is non-significant. They tell you the same thing. So this process is known as a univariate walled test. I use that term regardless of whether it's T or Z, but technically speaking, it's a Z thing. In the Agresti book, you'll read about this. So there's 3 ways to test for significance in statistics. There's walled tests, there's score tests, and there's likelihood ratio tests. We will do 2 out of 3 this semester. So we will use Z instead of T for this, but otherwise it's going to be the same idea. In regression land, here's how a standard error is made. It is the leftover variance in your outcome divided by the variance in your predictor times your degrees of freedom. So if you only have 1 predictor, this is what it would be. If you have more than 1, the denominator changes to add this extra part. It is the amount of unique variance in X. So all things being equal, standard errors are lower when X has more unique variance and when you have less residual variance. So your model is more right, and each predictor brings more to the table. So as predictors get more and more related, this thing becomes a problem, and your standard errors can get large. So when people worry about multi-collinearity, that's what they're talking about. It's not something you can fix, though. The more related your predictors are, the harder it is to say what they bring to the table uniquely. That's true. That's always going to be true. These will not be found as formulas in maximum likelihood land. They are products of second derivatives of the likelihood function, and that's all I'm going to say about that. Yes, calculus finds them.
Acceleration.
Because you got the height, right, of the mountain? This is a gesture thing. You got the height of the mountain. So mountains can be steep, mountains can be flat. If I have a steep mountain, I'm more certain where the top is than if I have a flat mountain. So how quickly it gets to the top, essentially, is an index of standard error in these models, where high standard errors would mean flat mountain, low standard errors means peak mountain. There, math. That's all I'm going to say about that. You got to take advanced courses, and you got to go over to the stat department if you want to learn more. Effect size. This is also something we want to report this semester as well, just a different way. We're trying to convey the absolute amount of relationship in a metric that is more readily interpretable and unit-free. So if I told you the slope is 3, that could be a big slope or a small slope. You got to know what the units are. 3 what? Test scores, years, temperature, like what is the metric that 3 is in? You have to know that. And effect size, you don't have to know the metric in theory. That's the idea. So in general linear models, the families that people use is like the standardized mean difference family, D, sometimes G, sometimes other stuff. The R family, or what is known as eta, also. So that ranges from -1 to 1. We're going to do something different this semester than either of these, but technically these would still be available to you as choices, just not as common. Standardized slopes I don't like. Here's a blog post about it. You can read for why. I didn't write it, someone else did. I'm not the only one who doesn't like them. They're ambiguous, and they also go away in these models too, so they're gone. Here's some formulas. So if you can get your estimate divided by your standard error, that thing can be a t. You can make a d, you can make a t, you can go back and forth. So you can always find effect sizes out of a hypothesis test regardless of what kind of model family you're in. Scaling, we're going to center predictors the whole semester so that 0 is meaningful. 4 reasons as already discussed: to maintain a fixed intercept that means something, and conditional fixed slopes within interaction terms. That's the other part of it. And I have this as an aside. In more advanced models, forgetting to center can break it. I have seen models not converge because someone centered or forgot to center and 0 was so far away from the data that it couldn't figure out one of the variances. So that can happen. So it's called centering if we're talking about numbers. We're talking about subtracting or adding a constant. Sample mean is a very common choice, but you could pick any value that's meaningful. I pick a reference one if there's a standard. The minimum value is nice because then you can talk about as x goes up. That makes sense intuitively. For categorical predictors, we're going to do the same thing but switch the terminology. We call this coding instead of centering. And the rule is if you have C categories, you need C-1 new variables to fully differentiate their mean differences. So if I have 3 groups, I need an intercept and 2 slopes. Those 3 things will give me the 3 group means perfectly back. I prefer the version where everything is binary into 0s or 1s so that there's a ready reference group interpretation. I don't prefer effect coding where the intercept represents the average because then it's not specific to any one group. That's a preference, but there are different ways of doing this. So you'll get to practice this semester as well. Here are 2 ways of doing this that we talked about last semester, just to review. Indicator coding is this one, otherwise known as dummy coding in the literature. I've stopped saying that. I don't want to say the word dummy. It doesn't sound nice, even if I'm not talking about somebody. It's binary or indicator coding. So in this example, if I have groups A, B, and C, I'm going to decide that I want group A to be my reference, and I want to talk about how B differs from A and C differs from A. Then I set up 2 new variables, and I named them for what they're going to tell me, A versus B and A versus C. So in the first column, I set A equal to 0 in both places. What that's going to mean is that my intercept is going to give me the expected mean for group A, because the intercept is when your predictors are 0. Then I turn on the first variable if it's B, and keep it turned off if it's C. So just this column right here splits A and C into one group and B into the other. That's why I need the second column to then resplit A and C. So when both are together in one model, this column, that slope, is going to tell me how B differs from A. This column is going to tell me how C differs from A. Cough, cough, bridge question. I can't say how A differs from B and have that be right. Order matters. Because the reference group is the one, like the way I do this is the 0. I always label it as the first one in my variable names. This is A versus B. What that tells me is how B differs from A as the reference. Otherwise, if you say it backwards, the slopes are backwards. They're in the wrong direction. So if this column has a positive slope, that tells me B is higher than A. If it has a negative slope, that tells me B is lower than A. Here's an alternative. This is sequential coding. I like this one for ordinal variables. Here, what we are doing is capturing successive differences as we move up the variable. So for an ordinal measure of how happy you are, for instance, on a scale of 1 to 5. I set the first level as my reference, and then each of the slopes tells me what happens as I move up one category. I find that useful. The difference between these coding schemes is whether the one stays or goes. So like right here, it goes. That means each of these comparisons is relative to the reference. Because these stay at 1, each of these is relative to the one before it. So that's one thing you'll get a chance to practice again this semester. You have seen it before. Here's some others that are in the regression textbook that I use in case you're curious. I've never used these in my life. They exist. How's that? In particular, like this nonsense with fractions, no. Just no. There is an article on your reading list that I really liked. It's linked right here, and it's covering how to set up categorical variables, and it presents some other choices that I did think were useful. So if you deal a lot with that kind of data, I would recommend taking a look at that article especially.
Is that a Joffrey and Freezy?
That sounds right.
Not linking.
It's what?
It's not linking.
It's not linking.
What it says like unavailable or something.
Hate it when that happens. Oh.
Let me see if this link is broken. Okay, so I don't know if this is a new thing with everything going dark in the world related to grants and research, or if this is a old problem, but it worked when I made it. That's what I know.
But it's the Joffrey and Freezy one, right? So we can go find it.
I was gonna say that's also in your files that we can download.
In
Yes.
Icon, under folder, under files, I have a zip folder of all the readings for the class, so it's in there. Yeah, I don't make you track these things down because I find that annoying. So I track them down for you and put them in a folder. So we've got access. But yeah, this is, okay. I'm not going to talk about that. But I am, we're all holding it together. That's what we're doing. Okay, so how is this feeling? Can we do a thumb check? Thumb up is feeling okay. Thumb down is like, I hate this. I'm hoping for somewhere above flat. We're doing okay? The Zoomers are saying they're okay. They don't have a thumb scale, but we do. Is this sounding familiar, at least? Yeah, okay. Because what I'm trying to do is like emphasize the things that are going to keep coming back. Like we're going to keep talking about slopes and estimates and standard errors and significance and all that stuff. We're going to have different kinds of predictors as well. 308. I think we have the strength for this. I think we do. Because this is not new, theoretically. So what if I have 4 groups? I need to make 3 new variables and give them slopes. Then I'll perfectly capture the 4 means. So my linear model would look like this, where D1 is this column right here, D2 is here, and D3 is here. If I were not in this class, what would someone else call this model, where I have 1 variable as a predictor, and it's categorical with 4 options? And I put it in to predict a continuous outcome.
Manova?
ANOVA, yep.
ANOVA.
Yep, because it's 1 outcome. It'd be multiple outcomes, it would be MANOVA. But yep, that's what people will call this. A one-way ANOVA, to be specific, because there's 1 variable, and that's the way, apparently. So in this, the model tells us what the mean is for each of the groups. Beta 0, because it's the predicted outcome when the slopes are 0 here, that's going to be the mean for the control. And then it plus each of the other slopes gives me the mean for each of the other groups. So beta 1 is a difference. It tells me how the first treatment differs from control. Beta 2 is a difference, how the second treatment differs from control, and likewise for the third. So in this analysis, how many mean differences are going to show up in my model like this? 3, right? I've got control versus each of the others. How many more are possible? I got 1 to 2, 1 to 3, and 2 to 3. So 3 more. What if I care about those? Am I stuck? Could I find them out? Yeah. And this is something that you may or may not have seen, depending on who taught you this. I'm going to show you how to get the missing things out of the same analysis. So let's put some numbers in the story. Let's say the mean for control is 10, this one is 12, this is 15, this is 19. Okay. If the model tells me what the mean is for each group, it has to be able to tell me what the differences are. Has to. It knows. So the way to think about it is like this. Control versus treatment 1. Well, I know this is the mean for treatment 1 as the alternative, minus the reference mean, which is beta 0. They cancel. I'm left with just beta 1, which has to be 2, because that's how treatment differs from control. If it were how control differs from treatment, that would be minus 2. Yeah, same information, but the slope has to go in the right direction for interpretation. The same logic gets us all the other control-related differences. As a general principle, when you set up your coding, the model parameters are going to tell you all about the reference group. They're not going to tell you about the alternative groups. But I can get there. So treatment 1 versus treatment 2. Here's the mean for treatment 2 according to the model. It's beta 0 plus beta 2. Cool. Here's the mean for treatment 1 according to the model. Beta 0's cancel, and I'm left with this. So there is a question on your bridge activity like this, trying to get you to recognize this idea. The difference between the slopes tells you the difference between the non-reference groups. So beta 2 minus beta 1, 5 minus 2 is 3. That is indeed the difference between the two. And I can do the same thing to get treatment 1 versus treatment 3 and 2 versus 3 as well. So all of the differences are in here if you know how to ask for them. But anything that is a linear combination of fixed effects has to be asked for separately. And I will show you how to do that if you don't already know. If you run things like EM means as an R function, and that they have that's what it's called in SAS, it's called LS means, and it's called that in SPSS, this is what it's doing for you under the hood. It's doing the math to figure out all the differences and how the model tells you. So we're going to do that. New topic, 312, good transition point. So we will pick this up next time. Any questions as we adjourn for the day? We had the strength to make it, we did. You're all awake. I win.
And you didn't drink any Mountain Dew.
We've got a bridge homework due on Monday.
That's right.
Have we covered enough that if we open it now, we can answer it?
Yes. I think you should be able to answer it when you walked in the door of this class. And to remind folks, you get 3 points for giving it a try. And you get 0.2 for every additional question you get right, up to 2 points.
You pass if you try.
Yes. And we will go over the answers as a group. So if you don't turn it in on time, you lose the chance to get the accuracy points because they will be public knowledge. But we'll talk about why the answers are the right answers. And hopefully if it didn't go well, then this will get you sort of situated to do better when it actually matters on your homework. It's a new thing. I'm giving it a try. So
And with the bridge, we're going to get 1 attempt.
1 attempt.
Okay.
Yep, 10 multiple choice questions. If you don't understand the question or you don't understand the answered choices, please let me know. I'm happy to clarify what I meant. Yes.
Is it timed? In other
No,
words,
not timed. Nope.
What if you open it and your computer restarts? Do we email you and say, hey, I'm sorry?
If you didn't submit it, I think you can go back and finish it.
Okay.
Yeah. Question, Leonard? No? Okay. All right. Well, then give that a try if you get a chance. Otherwise, I will see you Thursday.
Thank you.
Go.
Thank you.
Enjoy your birthday. Enjoy your day.